This video relates to finding the linear factors of expressions. More specifically, we're going to look at the difference of two squares. And this video will focus on expressions that are not so obviously part of the difference of two squares. So it's a slightly more challenging step from what we've been doing in class. So just a reminder, this is the difference of two squared, this is the equality. So if you have a number squared minus another number squared, the factorization of this is the first term plus the other term, and then the first term minus the other term without the square numbers. So you have the difference of two square numbers here, and the factorization is the terms themselves without the square, and then one bracket has a plus, one bracket has a minus. You could swap the brackets as well. You could have a negative first and then a positive. It doesn't really matter. It's the same thing. So first example is this. We have 3x plus 2, all of it squared, minus 9. Now it's not so obvious that you can actually use the difference of two squares here, but I'm going to explain how we can break it down. So the first term can be seen as a square number, so imagine this whole thing as your a. So 3x plus 2 represents a. And 9 can also be written as a square number. It's just 3 squared, so it can be represented as a square number. So we get the following. 3x plus 2 squared minus 3 squared. And we can write each as our a and b. So this could be our a squared and b squared. Which means now we can easily factorize these expressions. We open two brackets, one with a plus and one with a minus. And then I'm just going to take the terms without the square number. That's the key point here. So it's just 3x plus 2 that I need. So it's 3x plus 2. Then the other bracket has 3x plus 2. And then you drag the 3 as well. So be careful not to write 9. You're actually looking at 3 because 9 is 3 squared. So b is equal to 3. Now that I have my brackets, I can actually simplify it further. So I'm going to move this bracket next to 3x plus 2 because it's redundant. So 3x plus 2 plus 3, and then 3x plus 2 minus 3. Hopefully you've noticed that we can simplify these expressions even further. So I have 3x plus 5 in the first bracket, and then 3x minus 1 in the second bracket. And this is the full factorization of my expression. Again, we just rewrote the expressions in terms of something squared and then another something squared, and we just took the letters themselves. So whatever represented a and whatever represented b. Now, if you have your very obvious difference of two squares, which is x squared minus 9. This can easily be seen, as we mentioned, x squared minus 3 squared. So you are taking x minus 3, x plus 3 as your factorization for the difference of two squares. Now this 3 and this 3, they actually represent the square root of 9. So I can also write this as x minus 9, x plus 9. But then it seems stupid to just write square root of 9 because we know that square root of 9 is 3. That's why we just stick to this expression. Now, why is this useful? Well, what if we actually face numbers that don't have a nice answer to the square root? So numbers that don't have integer square roots. So an example of this, which is the easiest example we can go through, is x squared minus 7. So this 7 cannot be expressed as a square number. However, we can notice that the square root of 7, if we square it, we'll get back to 7. You can check this in your calculator if you want to, but it is a general fact. The opposite of a square root is a square, so you are meant to get back to your number. They are inverse operations. If you're not convinced, you can try it with, for example, square root of 4 times square root of 4, and that is 2 times 2, which is 4. Another example is square root of 9 times square root of 9. That's 3 times 3, which is 9. So whenever you square a square root, you always end up with the number inside. So square root of 4 is 4. Sorry, square root of 4 squared is 4, and square root of 9 squared is 9. So this is just to explain the first equality that I wrote. So square root of 7 squared is actually equal to 7. So we can actually write the 7 as a square number, because this is a square number now. This is something squared. That's what we want. So we can actually write it as x squared minus square root of 7 squared. These are exactly the same things. We just rewrote the 7 as the square root of 7. If you didn't understand, just rewind the video and try to listen to the explanation again. Now, we're going to do as we did before. We're going to open 2 brackets, and then I'm going to represent my a. This is my a squared, this is my b squared. And I'm going to bring in my terms, so x goes in there, and then I could put a plus, put a minus, and then I'll bring my b term, which is only the square root of 7, not 7. So square root of 7 and the square root of 7. And this is what we call the linear factors of an expression. Sometimes this is doable, for example in this situation, and sometimes you cannot find any linear factors. But once you see an expression in such a way, don't give up. Try to think, how can you change one of the numbers to be a square number and possibly use the difference of 2 squares. As a practice, you can try and fully factorize x squared minus 11, and I'm gonna give the answer in a few seconds, so if you can pause this video and try it out. So the square root of the 11 can be rewritten as the square root of 11 squared, because it's exactly equal to 11. So I can just rewrite this 11 as the square root of 11 squared, so x squared minus square root of 11 squared. And then I'll take my, this will be my a, this will be my b, so it's x minus square root of 11, x plus square root of 11. There are more examples in your book. Have a go at them and try the questions we will do or have been doing in class, and look back at this video. It's a good way to see how factorization can go even further, and how can you factorize expressions that don't seem too obviously factorizable.